Like the FA and equals 40.
Here. Oh, here? 40 newtons at 30 degrees. Is that what you're asking me?
Yeah.
Okay, yeah, sorry. Thanks for asking, because sometimes it's hard to see. All right. So what's FA cosine 30?
It's like 34.6. Yeah.
34.6, we'll call it. And the FAY? 20? That makes sense. That makes sense. All right. So they want to know what the acceleration is. So here's a question for you. In what direction is this box accelerating? To the right. To the right, right? It's going this way. How do you know?
Because it says force applied.
Well, the force applied is going like this, though. So why isn't it accelerating that way? Because why, Jacob? What'd you say?
Because the force of the earth is greater than what's pulling it.
So there's some normal force, right? And there's some applied in the y direction. But gravity is so big. Actually, it's not, but it's big in this case, right? Is that what you were going to say, Taylor? Did you have something else to add?
Well, is it y less than x? Is that anything to do with it?
Is y less than x? Like this part's less than this part?
Yeah.
It doesn't really have anything to do with it in this case. The game is, and this is something that I may not have articulated very well before, so that's why I like doing lots of problems. The motion, the acceleration, the net force in the x direction has nothing to do with the motion, acceleration, and net force in the y direction. They are totally separate things, which is why we break this force into pieces in the y and in the x. Okay? They are separate things. That's why we like to do two F net equations so that we can explain what's going on. So I'm going to write F net in the x, and we're just going to practice this because it's good stuff to do. What forces are acting in the x direction? FAX. Anything else acting in the x direction? Friction. Is the box accelerating in the x direction? We think it might be because it says that we're going to calculate the acceleration. You told me that we're going to calculate the acceleration in the x direction. So I think probably it is. So do you remember what we write F net equal to then? Remember we did this before. We said that remember we said that Isaac Newton was not the first person to realize this, but he's the one that gets the credit. Jerk. Okay, so acceleration equals F net over m. If we solve that for F net, we can say that F net is equal to? MA. Yeah, so we can just write that down. It's the mass of the box times the acceleration of the box. Okay, that's the F net x equation. F net y, what's acting in the y direction? Normal force? The force of the earth? Anything else? FAY is, yeah. Okay. This right here is the key to solving these problems. If you can set up your F net equations, then everything else is just, arithmetic. I mean, that's just all math. This is the physics right here. We can write this as MA if you want. That's the acceleration in the y direction. But what is the acceleration in the y direction? What did we just say it was? 0. So we can just write that as 0 if you want. That's cool too. Okay. What are we going to do? How are we going to solve this problem? Let's talk about a strategy and then we'll start doing stuff. What is it that we want to know? Acceleration. I'm just going to highlight it so we can see where it is. I want to know the acceleration. Do I know the mass of the box? I do. Do I know the applied force in the x direction? I do. Do I know the force of friction?
Yes. Yeah. Wait, do we?
I don't know.
Yeah.
We know it's the opposite of. It's 0.30.
Is 0.30 the force of friction? Read it carefully. What does it say?
Coefficient.
Coefficient of friction. Oh, we have to think about what that means again. It's been a while since we talked about that. Do you remember what that means? That coefficient stuff? Take a look back on your sheet, maybe. Yeah, and we're assuming this one's going to be moving, right? So the force of friction, there was an equation for it, I think. Did you put it on your bright red sheets? I think we did. What did it say? What did it say, Courtney?
Wait, on the what?
On that bright red, like the force inventory? I think the one you're looking at. Oh, pink, sorry.
No, I mean,
Cherry.
that's helping.
Yeah, okay.
Well,
Or maybe we didn't write it down. Maybe we haven't written it down in there yet. That's sad.
it's the okay, so it's equal to,
Mu. It's like what a kitty says.
it says mu sub k times the nat or the normal force.
Awesome. If you haven't written that down right now, do that because we need that. So, just kind of thinking through our process here, we know the mass, we know the applied force, but we need to know everything in order to find acceleration, right? We don't know this one, so we need to go down here. What? Do we know the coefficient of friction?
Yes.
We do. We know that. Oh, you don't need that. Oh, stinkers. My computer's being really goofy today. Let's see if we can get this to work. We know that. Do we know the normal force? No. How can we find that? Is it the opposite of the gravitational force? No, but it's related, right? Where on this board right now do you see normal force besides right there? You see that? Okay, so we're just kind of problem solving, making a plan here. We need to know this. We need to know Fn. In order to find Fn, what do we need? Do we have Fg?
Yes.
I think so, or something close to it. Do we have FAY? And we know what 0 is. So here's the plan. I'm going to let you work on this. Looks like we need to use this equation, that Fnet in the y direction, to solve for Fn. Once you know that, so that's going to be step 1, right? Plug that in down here to find out what FF is. Plug that in up here to find out what A is. 3 steps. Okay? Talk to your table mates. Work on it together. I'm going to give you just a couple minutes to work on that. I think you can do it. I believe in you. What is the coefficient? 0.3, I think, but I'll check. It was 0.3, yes.
The normal force.
Yeah, but what's the number?
There's no number, it's just like X.
Oh. So
There are no units. Is that what you're asking about, the units?
yeah, I thought.
No. This thing is mu sub k. It's the coefficient of kinetic friction. So as that thing is sliding.
Always equals and it's your.
So kinetic friction is equal to the coefficient of kinetic friction times the normal force.
So what about the other the
Static?
static?
Static is the one that's less than or equal to. We're going to do a lab. I think it'll make more sense. That sounds fair?
Yeah. Did you try? Oh, you forgot what normal force?
How are we doing over here? Not an answer?
Wait. That's so wrong.
Yeah, but you have to number. This is that.
We're trying to find them. That's how many people. This is
No. He says no. You're wrong.
F net y is.
Yeah, but what is gravity is not negative. Gravity is empty and it's -8. And then
Negative 1.5.
yeah. So then this is then zero. And then since it's negative, that's a positive. You gotta count the stop.
No, it's
I tree, I was doing this.
Check out gravity. You had gravity, you had 9. No, it's
Oh, yeah, in New York, like in New York City.
Does that answer the question you guys were trying to figure out?
Yeah. So
How big is your?
I don't know what you want to argue, so I can't tell you the right or wrong.
well,
It's gonna be 98 minus, 98.1 minus 20, so
The land is 300. House is 300.
alright,
Those are two very different lands.
I would try to find out.
That'd be a first one.
that's the one.
okay, or like lost or react.
Wait, like, one apart. That'd be like an $80 million house.
Yeah.
It's like 80.
85 better than
The way you wrote so then it's just kind of working backwards.
That doesn't exist. No, there's like.
elementary.
Yeah, and the fact that they're all interested. Keep me posted.
Where'd you get that? Wait, what? It's 1.12 meters per second. So your normal force is 78. Correct? Yeah. Then you subtract. You multiply it by 0.9. Yeah, and you subtract that from 22. If they're opposing forces. Friction is opposing the maximum.
So when you.
One, two.
One of them's negative.
Can I put that up there as like an asserted answer? I don't know what the answer is. You got what? 5.8? You guys should compare. Go backwards a little bit and see what you got. Did you guys get an answer? What'd you get? 1.12? Are you there? Still working.
Plus, what?
Don't you know what the
It's 34.6 minus 19.4.
Solve the problem. Yeah.
Oh my gosh, I know without you.
Yeah. And then it's 1.12.
So, okay, so I would not have thought of it.
And then you divide that by 10.
And then dividing it. Oh.
Did you guys forget to divide? See, this is, what's that? Oh, okay, okay.
The friction is in that. Then you divide by 10.
So Tate, what did you get for the force of friction?
Force of friction. 23.4 make you look stupid. I just said the wrong number.
I just, we just, we don't have the 78.
All right.
Wait, Harrison was the, not us. The location.
All right. What do we get, friends? 1.1? 1.2? 1.12? Units are?
Meters per second square.
Yell. She's like, no! Okay, let's back up.
Hey, we got that.
Okay, so stop. We don't want to fight about it. It's silly. Let's just do it and find out. Let's work backwards together and find out. There is a lot of stuff going on here. Some of my friends that are working on these problems just think they can just look at it, and I'm going to warn you not to do that. You need to write it out, if for no other reason than to practice, because this is how it's going to have to be done. But I want to acknowledge, like, there's a lot of stuff going on here. So I want to back us up. We're going to look at this equation. We were finding the normal force. Do we agree that it's 78.1 for the normal force?
Yes.
Is everybody okay with that? Okay, so we're all in agreement there. Fabulous. So we're going to take that normal force and put it in over here to the force of friction. So we're taking that 78.1 and multiplying it by 0.3. How are we doing? Are we okay there?
Yeah.
Question?
Is friction supposed to be negative?
Good question. That's what we need to talk about, isn't it? It's the negatives and positives. That's what's coming right now. So we need to look at this equation. I don't have any negatives and positives. All I've said is that these two forces have to add up to this, right? But we need to acknowledge the directions because forces have direction. So we need to pick. And honestly, you can pick something different than your neighbor. It doesn't really matter as long as everybody's playing the game appropriately. Generally, I think of the right as being positive. If you want to be that weird one, no, that's judgmental. If you want to be that different one that decides that positive is that way, the unique individual,
Yes.
you can make it negative, but then you also need to make the acceleration negative. Are you with me there? Because regardless of which way you say is positive and negative, we know that the force in this direction is also going to be the same direction as the acceleration. So I'm going to call this way positive. So I'm going to call my FAX positive. I'm going to call my FF, because it's going in the other direction, I'm going to call it negative. And my acceleration is positive. Paying attention to those directions does matter, doesn't it? So we're going to subtract 34.6 or 23.43 from 34.6. Okay? And divide by 10. Are we doing okay? I think that's going to give us something like 1.12. That sounds about right-ish. How are we doing? Anybody stuck or unhappy? Because I really want to make everybody happy. That's my goal. Do physics and be happy. Those are like the two things in life, right? That's it. Any questions on this one before I move on? Because I've got one more that I want to throw at you before it's time to go today. Go.
Okay, so if the applied force, this is going way back. Right?
That's okay. You're fine.
If the applied force was going up,
Yeah.
right, then you would like kind of do the opposite thing and you'd use the F net of y to find acceleration, right?
Uh-huh.
Because you had to use it to find the normal force, but then you put it into the F net of x.
Yes.
So right, it's I don't know what I'm trying to say. It correlates to like which direction it's going.
Absolutely. Yes. And the statement that you just made explains exactly why no two problems are the same. And we can't make assumptions that this one and this one are going to give you the same kind of thing, right? The rules are, the things that you know to do are to draw a free body diagram, to write down your FNet equations, and then it's just like a plug things in and figure out what you need to know. Okay? Free body diagram, FNet equations. Those are your two lifelines to solving these problems. Okay? All right. Here we go. This one's weird. I'm going to take everything that we just did and tip it around. I'm going to tip it onto an incline. Okay? So what I'm doing is that I'm going to take a ramp. So now instead of having this nice horizontal surface that we've been so fond of the last few problems, I'm going to take that and I'm going to tip it. Right? This takes some paying attention. This may be one of those things where the physics teacher, expert people say, why are you doing this at the end of the day on a Friday? That's a mistake. But you know what? I know that you guys can handle it. And I know that we're going to get as far as we can, and then we'll come back to it on Monday. We've got an applied problem that we will do with this on Monday, but we're going to start here, and then we'll look at this Monday first thing. Okay? So here we go. What's the first thing we do whenever we're trying to solve a forces problem? Free body diagram, right? The free body diagram is your key to happiness. So here we go. Shh. It says determine the normal force of this box sitting on this ramp, blah, blah, blah. So here we go. We got to draw a ramp. I would strongly encourage you for this free body diagram, because it's the first time we've ever done one on an angle, to draw it really large, like at least half of the width of your paper and at least, 7 or 8 lines deep, okay? Because we're going to draw it, it's going to be big, the bell's going to ring, and it's going to be great. So here we go. You guys have got this. It's going to be awesome. You're going to love it. I know you will. So I want you to draw your ramp. I want you to draw your box. Don't draw anything else yet. Okay, we're going to do this one together. So I want to make sure everybody's there. If you're not right now using pencil, you may want to get a pencil out, just because sometimes the first time you do it, goes a little haywire, and I want to make sure we're good. Okay. What forces are acting on the box? Raise your hand if you can tell me a force acting on the box. Go.
Gravity is pulling back straight down.
Gravity is pulling, right? And gravity is pulling it which direction? You just said it.
Straight down.
Straight down towards the center of the earth. This is the weird part, ladies and gentlemen. It's pulling straight down towards the center of the earth. I'm going to draw it really big because we're going to use that in just a minute. And I'm going to write it over here. So I'm going to say this is the force of the earth on the box. Oh, come on, stinker. I don't know why this just doesn't like me today. That's my FG. All right. Are there any other forces acting on the box? Short answer is yes. What you got?
Normal force.
Normal force. Normal means what? Perpendicular. So the surface is now like this. So that needs to go at an angle too. It's weird. It's weird, but I know you can do it. I believe in you. You got this.
It's unique.
It is a unique direction. So this is going to be the force of the surface on the box, Fn. Anything else?
Friction.
How do you know there's friction acting? It's not falling, right? If you have ever stood on a ramp when it's icy, like in the winter, you're going to slip and fall, right? Because gravity is going to pull you down that ramp. Absolutely. But it says this box is not going anywhere. So friction has got to be acting. Where is the friction acting? What direction?
Parallel to the going out.
Parallel to the surface. And it always goes opposing motion, right? So that's going to be up or down the ramp? Up the ramp in this case. So let's go ahead and draw that. Up the ramp. the force of the surface on the ramp. Oh, excuse me, force of the surface on the box, my bad. That's my frictional force. So, it looks kind of weird, I think. Now, here's the funny thing. I'm going to look back at the picture that we drew in the other one. In this free body diagram, do you notice that 1, 2, 3 of these forces are all acting perpendicular and parallel to one another? And there's one silly force that's acting at an angle, right? Okay, now we're going to look at our other picture. Which of the forces is the wonky force in this one? Gravity. But it pulls straight down. It does pull straight down, but everything else is parallel and perpendicular to the surface. You with me there? Yeah. So unlike the other one where we're just pulling, we're just playing with that force that was, at a funny angle, we get to break up gravity this time. It's a little strange, but we can do it. So here we go. This is the hard part. When you break up a force, the original force must be the hypotenuse of your triangle. Okay, let me say that again. When you're breaking up a force into components, the original force needs to be the hypotenuse of that triangle. Okay, so we're going to do this. We're going to break it up. We're going to have one part that goes perpendicular, and one part that goes parallel. My right angle is right here, so it is opposite of my original force. Okay? That's the hard thing to draw, but I think you can do it. Thank you guys for sticking with me on this Friday afternoon. I know this is weird, and I know it's Friday, but I appreciate the attention that you're giving to this, and it's going to make Monday so much easier. When we broke up the forces, we had that one coming up at an angle, right? We broke that, we called it X and Y. But X to me goes horizontally, and Y to me goes vertically. And so sometimes people want to tip that axis, and I want to tip the axis, but I don't want to call it X and Y, and I'll tell you why in just a second here. I'm going to draw myself an axis like this. Sometimes people want to say, oh, this is the X, it's just kind of at an angle, and this is the Y, and it's kind of at an angle. Here's the problem. What if the ramp was really, really steep? Are you with me there? Then the X would look like the Y, and the Y would look like the X, and then I'm just super confused. That makes me sad. We want to be happy. We want to do physics. That's our plan. So that's what we're going to call them. We're not going to call them X and Y. We're going to keep it simple here. We're going to call them parallel and perpendicular. Does that make sense? One of them's parallel, one of them's perpendicular. I don't care how steep it is. It's always parallel and perpendicular. Yeah.
It's always to the surface.
Yeah.
Okay.
Because these two forces are always based on the surface, right? Normal is always perpendicular to the surface, and friction is always parallel to the surface. So let's just use that since we've already got it. Let's just use it. So I'm going to call this one, right here, I'm going to call this FG perpendicular. And I'm going to call this one FG parallel. Okay. I'm going to stop there. You don't want me to stop? Don't we have really a minute left, right?
Yeah, we have 10 seconds.
Okay. Thank you guys so much for working hard. I will see you on Monday.